First of all, I would like to thank organizers for giving me this opportunity to present here, and I would like to acknowledge my collaborators in this work, Induja and Professor IISc. So I'll start with blowout. I'll try to give you some general idea about what is blowout. So means extinguish a candle by giving some blow. You might know all. So what happens during this time when you blow a candle? So due to the high flow speed, the resources gets reduced, and during that time, if a flame is detached from the anchor, it means this wick, and it doesn't reattach, then flame blows out. So it goes to this state. So this is called the flame blowout. I will give you another practical, more practical application of situation in blowout. So this picture, if you remember, last week Professor IISc has shown. So this is SR-71 Blackbird, which is used by US Air Force and NASA for their projects. So it has two engines, and you can see that at one engine, flame is detached and it is lower than the engine, so it gets detached. So this is another situation of blowout. Now, what can happen if blowout occurs in such situations? Suppose you are traveling and in some plane, and during that time one of engine appearance blowout. So I will play one video here. So this is a spaceship rocket SN9 by SpaceX. So this happens when blowout occurs. So yes, so you can see here that yes, at that moment this engine lost the flame, means flame blows out. Due to that, it cannot create the thrust. So when it hits the ground, it crashed. So having such disaster or catastrophic impacts, people, so it requires some early warning signals for such catastrophic phenomena, and this made it an active area of research for controlling the blowout or forecasting the blowout, and there are many works are going on. What we try to do in this work, we raise a question: can we predict the time of blowout? So to address this question, we analyze one laboratory scale combustor. So I will give some short description of this combustor. So what we did is we mix. So in this combustor, the mixture of fuel and air is burned, and as a parameter, we change the mass flow rate of the air. So what happens is we supply fuel and air, it get mixed, and it is burned in this combustor chamber. So there is an so this is called a blob body, which acts as, like in candle have a wick as anchor. So this blob body is the anchor which holds the flame. So when blowout occurs, the flame blows out in downstream. So for our analysis, we acquired two system variables. One is acoustic pressure fluctuations, that is acquired by a pressure transducer placed here, and another is the heat release rate, which is acquired by this red one. This is called photomultiplier tube. So this is a schematic diagram of the combustor I showed, and this is some prototype time series. So I will give some short description of this time series. So at this point, the experiment starts. So then combustor at some stable aperiodic state, and as we change the air flow rate. So air flow rate we are changing, that is means that can represent the Reynolds number, you can say. In earlier Professor Sujit was telling. So as we change the control parameter, it experiences this thermoacoustic instability in this region, and then further changing the control parameter, here blowout occurs. So since we are our aim is to describe blowout, so we will focus on this part of the data. So here you can see that. So this is this Q dot is the heat release rate fluctuations. So as okay, another thing here we are changing the control parameter continuous manner in time. So we are changing control parameter linearly in time. So at this point, the this fluctuations in heat release rate suddenly comes to 0, and here blowout occurs. So we say that blowout occurs as an abrupt transition from a reacting state to a non-reacting state. So before that there was flame inside the combustor, and now it lost the flame. So that is why it is reacting state to non-reacting state. So since this transition is abrupt, so to track it, to get prediction, we analyze this time series further. So we raise the question: can we detect the signature of blowout in any of the system variables? So here you can see that this is the time series of pressure fluctuations, and this one is the change of mass flow rate of air, which is control parameter in our case. So it is changing linearly, and this red dot, this indicates the time of blowout. So we calculated window. So we consider 1 second window, and we move the window in this way, and for some particular instant we calculated the short time wise, we performed the short time wise Fourier transformation and identified the frequencies. So our aim was to look at what happens there. So we find that this there are the presence of some significant presence of low frequency prior to blowout. So it has been also reported in literature, the appearance of low frequency prior to blowout. And so these frequencies are not any particular one, but it is within a range from 5 to 25 Hz. Then he constructed one time series by considering the maximum amplitude within that range for each of the window. For example, for this particular instance, so this is the maximum amplitude, and so it is placed here. So in this way, for different instances, we calculated this time series. So now the question is, does this time series have some trend? So this is another prototypical this amplitude time series. So these dots are the data from actual experiment, and this is some kind of trend. You can see that this trend is some oscillation is there, which is increasing and which ends somewhere nearby. Similar kind of trends we observed in stock markets before a market crash, and here also the frequency increases and it ends just close to the market crash. So here crash occurs. This trend is called the log-periodic oscillations, and which is the manifestation of discrete scale invariance in the underlying system. Likewise, here it is in the market indices, and we expect our case that will be in the this AF, means amplitude time series. I will give some short description what is discrete scale invariance. So scale invariance relation is this kind of relation where x is the scale factor. So if you squeeze it or if you extend it, this relation remains same. So one particular solution of this kind of scale invariant relation is the power law relation. And for discrete scale invariance, this relation holds only for particular values of x of this type. When x takes value of this, only then this relation holds. But in real life, what happens, or in realistic situations, x is changed continuously. So in that case, there should be some correction to this solution. When x changes continuously, then we can write f in this form. This is a periodic term, and by expanding this periodic term in Fourier series, we can, by expanding the Fourier series and truncating it to the first harmonic, we can get this kind of relation. So now earlier we had only Cx to the power alpha of for each x equals to lambda to the power I. Now when we changed it continuously, one correction term appears. So that is why it is called log periodic correction to the power law. And this in turn gives prediction to the stock market crashes. Now the question is, does log periodicity actually exist, the data that we are observing? So for that we do some analysis. First, what we did, we retained the power law, some trend from the data. So these are the two different experiments I have shown here. Then the detrended series, time series shown some oscillations. The power spectral analysis of this oscillation, this detrended time series shows some peaks, so which signifies that log periodic oscillations are there. So this power spectral oscillation is done in the log scale. Now, how did we get this power law? So to identify the underlying power law, we calculated the doubling time, and we find that as we approaching the blowout, this doubling time is reduced. So which, like earlier in the morning Induja discussed, this is a so this gives the hyper-exponential growth in AF. So the AF can be approximated by this form. Further, we perform one non-parametric analysis to identify the presence of log periodicity. So here we, for each time instances, we calculated the maximum of the amplitude from the past and minimum of the amplitude from the future, and we subtracted it. So the idea is that if there is a change of slope, or there is some oscillation, in that case this curve will hit 0 and start grow again. So in that case, in this way, we identify two oscillations for both of the times, or both of the experiments, and again performing the spectral analysis, we identify some peaks. So we are convinced that there is log periodic oscillations in the amplitude time series in prior to blowout. Now we are at the state of doing prediction. So for prediction, we propose one log periodic power law. This is the form of log periodic power law, and so this is, as I said, this is the correction term, and this curve actually approximates the amplitude, and by fitting this curve to the time series will in turn give us this TC, which is the predicted time of blowout. So here are three different experiments for three different rates, and as you can see that, so this the dots are the data from experiments, and this red one is the log periodic power law curve. So this trend, so there is some trend present in the data which ends at TC, that is when you can say blowout occurs, and there is some comparison between the actual data. So this one is the actual data, and this is the predicted value that we get. So before saying more about that prediction, I would like to highlight about or say something about what is the physical insight or appearing of or emerging of this kind of law in the time series. So there are in literature before for blowout, two phenomena have been reported. It is like blowout is the kind of extinction of flames by the formation of global flame holes, and before blowout, it has been observed that the number and frequency of extinction and reignition events are increased as the system approaches a blowout. So it can be, it is not very clear here, but can intuitively seen from here. So there are some instances where the system, so there are some extinction occurs, like here, and it reignites. So this process continues, and the time between the extinction and reignition gradually means decreases as blowout appears, and here we can get the blowout. So, and it can be said that blowout occurs as a collective behavior of local flame holes, which led to the formation of a global flame hole, and which in turn gives the blowout. So it is like that. So for example, at these instances, at these OX, you can observe extinction event, and as these valleys, you can observe reignition events. So that number of this extinction and reignition increases, and at this point, so there are not enough fuel or not enough to burn or to means reignite. That's why the actual blowout occurs here. However, these things are in some, so this is kind of a hypothesis that we need further investigation to confirm. Now the prediction part. So what we can, so what this log periodic power law do for data? So suppose we are standing here and we do not know what is going to happen here. So this kind of log periodic power law can identify the underlying hierarchical structure, which ultimately ends when discrete scale, when blowout occurs. And by considering this much data, you can actually predict the time of blowout. For example, in this case, your actual time of blowout that you obtained from experiment is 38.5 seconds, but blowout occurs in 38.8 seconds. And by adjusting this boundary, you can say how much close we are to the actual time of blowout that is shown here. So for some given threshold, you can say that blowout can be predicted very well, even 5 or 6 seconds earlier. So we are not only getting in kind of early warning to the blowout by identifying the underlying hierarchical structure, we can actually predict the time of blowout. Now the summary. So how we are identifying the blowout? So it is the point where a system or a combustor goes from a reacting state to a non-reacting state, and that we identify it by when heat release rate becomes 0. We found that low frequency oscillations are present prior to blowout. So signatures of log periodic oscillations in the amplitude time series, revealing the underlying hierarchical structure of the data, and which in turn can predict the time of blowout. Yes.
Go. Please. Question?
Hi, this is actually very cool work. I'm wondering whether you think this sort of log periodicity is a generic phenomenon that would occur in other systems as well.
Yes, actually means many complex heterogeneous system it has been observed. Means for many stock market crashes, as well as in predicting earthquakes, oil prices, means mostly in economic markets. And so in earthquakes also it has been observed, but the main, so the most of the work done by Didier's Hornet, but still he has some doubt about what you say, it's generic feature.
Thank you.
But
so just before epileptic seizures and before some acoustic ruptures or something, multiple scenarios. There is one book why stock market crash. And then many examples are given.
So can you go back to the slide where you had the range of the TC, this one.
Yes.
So I'm trying to understand why very close to the 0 point, like very close to the TC, the actual TC, the prediction is not good.
Yes.
Yeah. Why is that?
Oh, this point.
Yeah. If you're away, like if you're too far away from it, you are not predicting it well. That I understand, but why is that happening? Is it because like at the TC, this is blowing up? Just trying to understand.
I also don't have much idea, but what we did, we considered the data and let the system decide what is the optimal point.
Try to answer. So if you are taking data more and more close to blowout, the fitting is getting like you are almost capturing all the peaks, and then it is expected to blow. The blowout is expected to happen at that TC, but in reality, what happens is flame is becoming more and more unstable, and it is like trying to get reattach and all, but you won't actually reach that TC. It's like before actual tipping point, it can blow off, right? Yeah. Yeah. So based on the signatures, it is actually predicting the real expected tipping point, but in reality, flame is undergoing blowout slightly before. I expect that is the reason. I don't know. Can you this correct?
So is there any other question? No. So let us thank Ankan for his talk.